Hello? Can you hear me? Thank you, Lisa. Good afternoon. Of course, one of the challenges for the afternoon presenter is to keep you guys awake after the beauty of mathematical models that they can be universal in so many orthogonal fields, relatively independent. There is yet another field where survival analysis is the key point, which is called, at Ford we also have we actually have a division called Ford credit. So what do they study? They study the probability of a defaulting on a loan, right? So as you come to buy a Ford car, there is the usage profile, right, of a potential buyer, and then look at your usage profile. They say you are trustworthy or not trustworthy, right? So let's do it quickly. What would be the response variable in the credit loan application, which is equivalent to these two? What is that duration? Time to default. It's time between the loan origination time and the time a given customer defaults on the loan, right? Unable to pay. What would be the censoring variable in the credit risk studies? Customers who did not default and they keep paying, right? The only thing you need to know, you need to know the duration of their loan, right? What would be time-independent covariates? And this is actually most important for them. These are the covariates that they use to actually make a decision whether to give you a loan or not to give you a loan in credit risk. It's your social status, right? Jobless status, binary, 0, 1. Either having a job or not having a job, right? Could be race in some extent, but I don't think so. Maybe not such a big factor. Age, etc., right? Time-dependent covariates in the credit risk studies. Economics, the economics, the jobless rates as a function of time throughout the country. Competing risk. What would be the competing risk analogy in the credit risk studies? In other words, what are the reasons for you to default? Exactly. Other debts, mortgage, unexpected loss of job, etc., right? And what's the failure avoidance strategy there? Insurance or having a good financial consultant, right? Who actually is trying to make sure you don't default. And risk containment, I guess there is no explicit equivalent, or is it, for risk containment and credit risk? You know, how about second job? You get a second job which is paying even higher than your regular job. So maybe that's a risk containment. Anyways, so hopefully I convinced you that again, the fundamental mathematical model remain, but all these parallels could be drawn between multiple industries. So finally, survival regression. This is the model that I want you. It sounds fancy, but if you look attentively, I will explain it's not that fancy. So what we have here, S as a function of time, S for survival function. What is the equivalent in our field for S? What is the letter? R for reliability, right? And so what's interesting about this model is that usually we would look at the reliability as a function of time, or they look at the survivability as a function of the age of the patient. But you see this conditional X, and X is that set of explanatory variables or covariates that explain, in a sense, why for certain subpopulations reliability is high, for certain is low, or survivability in the human fields, right? So once again, X is would be in medical field, in biostats. It could be gender, race, occupation, having a transplant, heart transplant, etc., right? So again, what's beautiful about this model? That not only does it allow you to model your underlying variables such as time to failure, mileage to failure, but also it allows you to introduce additional factors into the same model. And in fact, you will later see it also lets you know whether or not these additional factors are statistically significant, whether indeed they have influence. Are they influencing the probability of failure? They're not influencing the probability of failure, right? So it's just another extension to this model. And once again, like I said, the mathematical formulation for the fixed covariates, it's basically, so first of all, in this model, you recognize that the reliability, nothing new to you, is e to the negative cumulative hazard. The integral of the instantaneous hazard is the cumulative hazard, right? So we know this equation by heart. But again, the hazard itself is made dependent on the set of those factors, on the set of those covariates. And if these are fixed covariates, then you basically decouple your overall hazard into the so-called covariate independent hazard, or the baseline hazard rate. Basically, there is a baseline hazard function. And then you simply have a multiplier, a scalar, that depending on the value of that additional factor, it actually rises that hazard function up or down. Either increases its gradient or keeps it constant. You know what I mean? So baseline hazard, and it's easily scaled. Yes, sir?
Why is it always exponential?
To make sure that this quantity is positive. It's to reinforce the because if I don't, I need kind of mathematical operator which makes my function a non-negative function, because after all, h is the conditional probability. You know, the probability is always between 0 and 1. It cannot be -5. Just a convenient mathematical function that enforces positivity. Okay? So now, these are time-independent covariates, fixed covariates. There is time-dependent covariates, where now my x becomes a function of time, of the same time, as the let's say, as a function of the age of the patient. So this is the biostats constant context. Now let's move closer to engineering. What I have here, I have a non-parametric estimates of the underlying probabilities of failure as a function of time. I think it's months in this case, months on service in the field, right? For one common component here. Again, for the sake of confidentiality, I'm not disclosing the type of the component, but think about a water pump or some kind of mechanical component, which is common across multiple vehicle lines. You know, it's called, what is it called? There's a term for that. Universal applicability, but no. I'll come up with a term. But basically, when you reuse one and the same component, irrespective of the application, automotive application, right? But what you notice here, and by the way, as you look at this, again, this is nothing but a CDF, cumulative distribution function, or basically probability of failure, cumulative percentage failing. As a function of time, as you can see, we have basically underlying increasing hazard rate, right? And by the way, never mind this flat section. This flat section meaning that I had the latest observation here. And from here to here, I didn't have any more failures. So strictly speaking, this flat section, all this curve could be truncated at the point where they are bending. So don't be confused. Consider them as a set of probability of failure curves. But what you notice here, that despite the fact that this is a common component across multiple vehicle lines, you still have distinctly different behavior, right? And who knows, maybe this behavior is caused by the duty cycle. For example, even if you take the population of Tauruses, you take the Taurus that you sell into regular residential retail, and you have Tauruses that you sell to the police fleet. Of course, then, the one and the same component could be failing much more rapidly on the police subpopulation of Tauruses than on a regular population of Tauruses. You know what I mean? Just because of the heavier stresses, heavier duty cycle, etc., etc. So the thing becomes, so now I have a dilemma. On the one hand, I know for fact this is one and the same component. Moreover, it's one and the same failure mode. I know for sure, because when the failed part comes back to me, I could see the failure mode is exactly the same. So therefore, intuitively, I'd like to use one kind of probabilistic model, such as Weibull or log normal or any other distribution which can capture its behavior. However, I have another dimension here. I would like to capture this variability across multiple lines within one model. And what becomes convenient is the same survival regression, but expressed in engineering terms. First of all, you notice that I replace S with an R. Now it stands for the reliability function, right? And then I also have a function of time, i.e. underlying time to failure. But also, I'm now introducing this I generally refer to this as a vector covariance because it could be more than one factor. It could be the differences in the duty cycles, differences in the climate conditions where the subpopulations are used, differences even the assembly plants. Maybe one assembly plant produces lower quality product for whatever reason than the other assembly plant. So therefore, theoretically, you can have as many factors as you wish, but the beauty is that it's all combined in one model. The basic variable plus these additional factors. And so now the question is, how am I going to model the influence of these factors? And one of the common solutions is basically, first of all, I don't know if many of you know, this is, I refer to as a Meeker notation. In Meeker and Escobar, they come up with a convenient notation where they classify all the basic distributions such as variable, log normal, log logistic, extreme value distribution into the so-called location and scale family of the distribution. In other words, they use one simple transform where they say, okay, roughly speaking, this is the location of my failure distribution, which is like average, right? And this is the scale of my distribution. So if you look attentively, the way I introduce covariate into this model, I make the location of the distribution being dependent on the value of this additional factor that I introduced. In this case, vehicle line, right? And then in this case, I'm just assuming a simple linear relationship. And who knows? I'm going to process my model, see if these coefficients come back as statistically significant. If they do, it means that I guessed that relationship correctly. It means that it works for all practical purposes for the approximation. So, but before I go from here, I'd like you to think and tell me what other popular reliability model, and I'll give you a hint since this is a ReliSoft type event, I give you a hint. ReliSoft has a special module dedicated to one particular case of survival regression, where they model not only the cycles to failure, but also additional factor. What is the name of that module? Alta. Exa, who said that? Okay, is Doug Ogden here? He must be somehow recognized that. No, this is Alta. And by the way, what additional factor do we use there? Is the stress level, right? So I'm modeling the time to failure in the presence of the stress level. So stress itself becomes this additional variable. But in my presentation here, I'm just expanding it beyond just the stress. It could be, like I said, it could be geometry of the design, assembly plant, etc., etc. So here is my quick statistical analysis of this model, right? And as you can see here, these are, by the way, here's the estimate of my location parameter. Okay, here is the estimate. The intercept combines in itself the estimate of the shape parameter shape and location parameter here, right? And these are the individual coefficients for each of the individual vehicle lines: 1, 2, 3, 4, 5. Okay, and what you observe here, first of all, you see that all the coefficients, including the coefficients of the underlying model, come up to be statistically significant. The p-value is very low. In fact, frankly, I always prefer the t-ratio of z-ratio to look at the significance of the coefficient. Why? Because again, it has it can be viewed as an engineering metric. Those of you with double E background probably know what the signal-to-noise ratio is. How many of you know signal-to-noise, right? So signal-to-noise, if you think about it, what is Z here? Right? Z, or in some tests it comes as a t-ratio. It's nothing but the ratio of the coefficient to its standard error. So think about this as a signal, and this is your noise. If this ratio is high, then the p-value is automatically going to be low, and therefore the factor is indeed statistically significant. So all I'm trying to say that they did come up to be statistically significant. It means that by using that simple linear relationship between the location of the distribution and the value of the factor, I'm able to capture this phenomena. Now the question becomes, remember, in this model I have two pieces. One piece is baked into this structure. basically the underlying distribution, such as, once again, the underlying time to failure distributions. What distributions do we know? Exponential, viable, normal, etc., right? And the second statistical piece is this little linear relationship which just models the location of the distribution. But the question, when you start running this analysis, the question becomes which underlying distribution to select, whether it's viable, log normal, log normal. And for that one, you use the so-called Cox-Snell residuals. First of all, what is a residual? Residual is the error in the model, right? How far away is your predicted value from your actual value, right? For the Cox-Snell residuals, when you put them on the exponential probability paper, now don't get confused. This paper here is the exponential probability paper, but you're still testing, in this case, the adequacy of log normal distribution. It's just you're putting residuals, you're plotting residuals on exponential paper, right? And as you can see, the fit is pretty good, relatively good, except of course you have this strange deviation in the left tail. And by the way, that deviation is only true for about less than 1% of the lower 1% of the population. But still log normal. What if I change the underlying distribution to a different one? Look at the Weibull one. Huh? This is a textbook example for good statistical practice. In fact, I will have to ask the copyright later from from Eliasov to see if I publish this indeed as a textbook example, right? So all I did, I just changed the log normal underlying to the Weibull underlying, but my structure was still the same. This is the same structure, right? So as you can see, I get a very good distribution of the residuals, and here's my final answer. So now I can model all these individual probabilities of failure within one model, which is using the common failure mode, common underlying distribution. It just has this discriminating factor which helps to discriminate between these two curves, right? So this becomes very accurate and convenient prediction of the future probability of failure. And in fact, I mean, for practical applications, why did I remember these curves look like this? Basically, all I did with this model, I extrapolated each of these curves respectively with a pretty good accuracy. In fact, if I overlaid these curves onto the extrapolation, you would see that they extrapolate pretty accurately, right? And extrapolated them all to 60 months in service, which is 5 years, and now I can translate this into financial. Whether I want to extend my warranty by that much, then how much will it cost additional from what I have now, etc., etc. So it has lots of practical implications. Okay, so I have about 15 minutes left, but I promise not to hold you anymore. Just one level up of difficulty. So remember I told you that we have all these examples were the so-called fixed covariates, concrete parameters of the design which are influencing the probability of failure in the field. This is a case study which is showing the influence of the time-dependent covariates. So now I have this additional factor which is influence probability of failure, but that factor itself is time dependent, and it makes it convoluted because I'm measuring my reliability function of time in service, and this covariate also changes as a function of time in service. So kind of confounding, right? What this case study practically is about is the so-called TSB. Anybody knows what TSB is? What is it? Perfect. Technical service bulletin. You know that it's common practice across automotive, and I think not only automotive industry. If the manufacturer finds a defect and a quick solution to that defect, and of course, if the defect is not safety critical, we inform our dealers. We publish these technical service bulletins, basically saying that, so that component X has this potential problem. So next time the customer comes back to the to your dealership for oil change, please check out that component. If it's okay, leave it alone. If not, please replace it. And again, I once again say this doesn't concern safety related. It's just what we call customer satisfaction defects, right? But what we observe from the reliability side, when we start analyzing this data relative to a given component in the field, we notice that its hazard function has almost a step function change. It goes low, 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 then jump. Low, 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 jump, etc., right? And that jump, depending on the age of the vehicle, in my little notation here, my means the vehicle, warranty start date, that is when the vehicle was sold. My circle means failure date, and my triangle means censoring date. But you see, but there is a non-random date of this when the TSB was published. Basically what's happening, that now that dealers know about this, if they didn't know, my failure rate would continue homogeneously as it goes. And in fact, I would be measuring time to failure. But now that the dealer knows, right, then I have elevated rate of replacements out of a sudden, on a relatively healthy component, but they know and dealers, of course, never miss an opportunity to actually bill for, to charge for additional claim. So they would generate this this claim. So our statistical problem is now, how do we, in the presence of this time-varying covariate, how do we still assess the expected warranty cost and set aside a needed budget to cover for that, right? And the way to do it is the survival regression. Again, I have my underlying baseline hazard. I still have the same structure, but now my vector is time dependent, right? And so this is again a fancy slide to show that once I computed that time dependent hazard rate, I'm now able to predict the number of failures for subpopulation of vehicles having the same age, basically having the same warranty start date. And the kind of practical implementation, if there was no TSB, there was no external non-random influence, I would have one curve characterizing the probability of failure in the field. Now, depending for different groups of the vehicles, these different lines show basically different groups of vehicles having different warranty start dates, basically having different birth dates, right? So I'm monitoring the population of vehicles of the same age, and as you can see, now they behave differently. So this starts growing right away. It means that it hit the TSB influence shortly after it was produced, right? Whereas this one was going and then it hit the TSB influence, right? By the way, the same model could also be used to model seasonality, because if you think about it, seasonality is also a time-dependent covariate, right? Depending, let's say if you have a summer failure mode, if this population of vehicles, subpopulation of vehicles, hits the summer right away, and this population of vehicles was produced in January, so it takes about, well, let's say here, in January it takes about 6 months before they start seeing this summer influence. By the way, in one of the ReliaSoft newsletters, there is a very interesting article how to model seasonality based on the underlying duty cycle of a cycling profile of a component, which is also can be used to model seasonality in the framework of the accelerated life model. So that's it. Once again, my purpose here was to attract your attention to this survival regression model, which, like I said, may be quite useful. It's very useful in the biomedical studies. You will find it useful, hopefully, in the engineering studies as well. Thank you for your attention. Do we have any questions? Wow. Okay, Bob, you promised me a question. Come on. Okay. Okay, yes.
Thank you very much, Vasily, for explaining these difficult concepts in a very easy to understand way.
Thank you, sir.
Thank you very much. I was in Ford when the Firestone episode happened. So you
can prove that we actually use these models.
Exactly. So I was very much excited that it was a very good reliability breakthrough, as you said. But now, in hindsight, could you have used DOE, design of experiments, to identify the critical factors, since the purpose of the experiment that you performed was to identify which factor was critical? Could you have used that instead of doing survival regression?
Excellent question. In fact, I feel sorry that I didn't use this question to challenge you guys. No, this is an excellent question, because think about it. So basically, all we did in this experiment, in this study, we studied the influence we study the influence of these factors on my response variable, right? As simple as that. I have a response variable and I have a bunch of factors. So, indeed, why didn't we use the DOE? DOE would have been such more coherent and convenient. You could have. I mean, you could connect the DOE structure through the hazard function. That's no problem. There is a bigger factor. Think about it. Yes, sir. Exactly. Well, so think about it. Look at the nature of the components. For me to do a DOE, I would need to select the components with the wedge gauges conveniently at the lower level and then conveniently at the upper level. Same thing with the peel force. How do I pre-select based on the peel force? Because you see, what happens here, due to my instrumentation, I'm measuring these factors post-mortem. You know, once I have my response, in DOE, what do? You plan it first, and then you run. In this case, I run it first, and then whatever happens to be my factor, it's my factor. I'm stuck. You know what I mean? I mean, peel force, I told you, the peel force, I need to take the part of the tire, cut it apart, and very accurately start peeling and measuring the peel force, or centigram of the peel force, and then average it out, right? In my case, due to this instrumentation, as soon as the one little piece of the tire goes into thread separation, in other words, the crack starts propagating between the two belts, I say stop. I go to the opposite end of the tire, still healthy, and I cut it apart, and I measure the gauges, I use the peel force. In fact, this question is good not only for this study, in general. Why do we use regression analysis as opposed to orthogonal DOE analysis? Orthogonal DOE only when you have your luxury of conducting experiment. If you're doing any kind of post-mortem or population-based responses, you are stuck with regression. But excellent question.
So orthogonality is the issue there.
Absolutely.
Exactly.
And of course, we did check. These factors were reasonably orthogonal. In fact, you may have noticed. Why do you think the tire age didn't come up at all? You would think, wow, the older the tire, sure, should be influencing the probability pair. Why? Because it showed a collinearity, internal correlation to, I forgot I think it was to the peel force, I think. It was heavy internal correlation, right? So therefore it throws away. In DOE, you are guaranteed independence. You can place. So basically, to answer your question quickly, it's a field-based data set. I don't have a luxury of going and pre-selecting my tires conveniently.
Thank you very much.
Thank you, sir. That. Yes.
If I'm following your line of discussion correctly, the other problem is the difference between running a DOE where you have to be right about the variables you choose, and the Achilles heel is you will actually miss something that you didn't know was there that was a predicting variable, as opposed to what you were saying about actual produced product. It contains the condition.
Exactly. It is already subject to those noise factors, which are baked in there, so to speak, right?
So whenever you have actual parts to do the analysis on, if you revert back to DOE, you're reverting back to guessing.
Right.
Because you're doing what you think, and you want to find out what you don't know.
Right. Exactly. So in this case, Bob, this was data coming from the ultimate key life test. Not the key life test that we designed at Ford, but key life test called the field. All the noise factors are baked in ultimately, right? So, yep. But excellent question, thank you. Any more? If not, enjoy your coffee, and you can always find me. I'm going to be sticking around through the rest of the conference. Thank you.